done with chapter 10. Just one more formula. I want to make sure you guys see. And it's connected to the kinetic theory of gases again. But that last formula in chapter 10 officially will be over. It's designated as chapter 10 material. The chapter 10 homework and quiz are currently slated to be due. I did fix the date, Tuesday the 9th. I keep that in mind. The chapter 11 assignments are up and they'll be due later on the 16th. So today we're going to start chapter 11 and we'll finish it up by the end of next week. Although it really is just more of the same. This whole section is just heat and thermo, and the book arbitrarily divides it into those 3 chapters. But because it's how the book divides it up, that's how the homework's divided up, and I want to stick to that. While I have the calendar up, I have decided on the preliminary test dates. The first test, and I'll write this on the board because I'm going to forget myself, actually. These dates are tentative. They will be adjusted if need be, but I will not, if they need to be moved, I will never make them earlier. You always will have, whatever I tell you, you will only ever have more time to study. Personal practice of mine. So, yes. Our first test, presently, I've decided that it will be administered, well, it'll start to be administered on the 23rd of February, which is in a couple of weeks, but this first part of the class, the heat and thermo part of the class, is pretty self-contained. It'll be mostly review for everyone who's seen this type of stuff in chemistry. So I want to keep all of that contained in one test without having to add too much else on it. And if chapters 11 and 12 take a little longer than I'm thinking they will, I will push that back if I have to. But presently, we're looking at Tuesday the 23rd. On that day, what will happen is we'll have class, we'll review everything that will be on the test, and then it'll open up to be taken on WebAssign. Once you start it, you'll have 5 hours from when you first open it to when it stops letting you change things. Because it's meant to be a 1-hour class, but everything takes longer online.
And you have to do it sometime that day, after class?
Since this class doesn't meet Wednesday, I will leave it open from the 23rd till midnight on the 24th. Basically, just have it done before the next class period. That way you have as much time, many options as possible for having the test when you need it. And I'll probably be in the habit of not having labs during test weeks.
Oh, okay.
So, if that was your question, cool, yes.
How will we go about that with, like, our work?
I have been having students simply send me scanned images of their work. So, email with your name, and within the subject line, your name, what test it is, your work, and whatever the machine doesn't give you full credit for, I will go in and assign you partial credit and I'll try to leave notes. I'll reply to your email with whatever grading notes I would have left on a paper test.
But after the test, even if we get it right, you just want all of our work?
Yes, in general, all of your work, just in case.
Okay.
And part of the 5 hours is so that you can email me in that time, and I will have time to get back to you, and you will have time to do something with that information, questions that you have. Notes, calculator, etc. You have access to those. The second test is going to be about electricity and magnetism. And I'd say most of this class in terms of weeks is going to be some type of electricity and magnetism. And so the next test, currently, well, this is the second of 2 tests. There's only 2 non-exam tests in here. It'll be Tuesday. We'll open up with the same rules, April 6th. And the test won't be any longer, because normally we have 1 hour in here to take a test, so similar number of questions, same level of difficulty. But since most of the class is some type of electricity and magnetism, there's going to be a little more time between the start of the course and test 1. Sorry, there's a little more time between these 2 tests than there was between the start of the semester and test 1. They're about 1 month compared to a month and a half. Again, that won't affect the amount of questions on the test. I just want to let you know about that in case you think shouldn't be about a test by now. In case this feels like it's close to the end of the semester. I like to keep the chunks of the course as separate as possible, rather than having one test that has a little bit of heat and a little bit of electricity on it. Save that for the final. So I do this to keep everything subdivided, and after test 2, we'll cover probably a little more electromagnetic field stuff, also light and sound, and that's just going to get factored into the exam. There won't be a dedicated test for it. Yes?
Did you say that for the exam, is that also focused on? Or is that?
I was leaning towards that, but
About if we could,
since we haven't assigned time for that, I may have everyone in a call taking it at the same time. Just to
Oh,
keep
it's
that
still
possible.
online though, like,
Yeah,
okay.
because in granted, last semester was the first full quarantine semester. I had students who had to leave campus, couldn't come back. They kind of had to do it remotely. So I'm trying to plan around the worst case scenario. So these are the 2 dates. Since it'll be online, I hope this shouldn't prove schedule problematic for anybody. If it does for any reason, let me know. I can change a date for someone specifically if they need it. And the 5-hour time should also help with academic accommodations as well. Words, how do I say them? What were the words I was going to say? I'll come back to them later. So keep those recorded, and I will be reminding you as the dates draw closer. Any questions about that information before we proceed today? Or any questions about anything in general? Okay, so let's real quickly finish up chapter 10. This is actually not a very new formula because I showed it to you at the beginning of this set of notes. We're just going to use it real quick before I load up the chapter 11 notes. This does relate to the kinetic theory of gases because we tend to use this formula when looking at specifically the velocity of particles in gases at specific temperatures. Again, all of the atoms that make up a gas have mass, they are moving, and they are at some temperature based on that movement. So this formula is just relating the kinetic energy formula scaled down to individual molecules and relating it to the temperature of the object. This temperature has to be in Kelvin, mass is always in kilograms, velocity is in meters per second. And this, Kb, is a constant called Boltzmann's constant. It is always the same number. This one's a freebie. if you're all familiar with the actual scientist called Heisenberg and the uncertainty principle, you probably heard that it's impossible to know the location and the velocity of a particle at the same time, which kind of makes this a little bit pointless, because, not pointless, just difficult, because if we can calculate this velocity, it is not assuming direction at all, or location, just the velocity of the particles inside of an object. So, we know we have approximated the mass of a proton. Good luck putting a single proton on a scale. And technically, single protons are a form of hydrogen gas, which I have to remind myself usually. And there's some hydrogen gas in this room, probably not pure hydrogen, because that might be a little dangerous, but there are definitely protons in this room, and we're just going to assume this room is at the average scientific temperature of 25 Celsius. In those circumstances, what would the average velocity of a single proton, H plus gas, be in this room at this temperature?
What is the line number v squared?
Good question. That line over anything typically means that that number is a vector. So out of everything in this formula, velocity is the only vector present.
I went under. Or is that?
Depends on who's writing it.
Oh.
It can go in either location. I've also had vectors denoted by writing a number next to whatever axis the vector is in with a little hat on it. But nothing else in this formula is a vector. So since the velocity has a direction, normally when you square that velocity, the direction just goes away. And that's why we might know the velocity based on this calculation, but not the direction. So this single proton, how fast are we looking?
I had a really big number. I had 2,729.
And by the math, that is correct. Now, this would be the fastest any element would be moving at 25 Celsius, because a single proton is the lightest element. Most things in the universe aren't single protons. So, say if oxygen was like 32 times as heavy, you divide this by 32. But that'd still be a pretty big number. Keeping in mind that meters per second is pretty quick. 1 meter per second is like average human walking speed. It's about 3.5 feet per second. So, why do we not detect this? If most of the particles in this room are moving at 1/30th of that speed, that would still be like around 10 or so meters per second always, and yet we never noticed it. Because of the ideal gas law, we assume that the particles are bouncing off of each other, and this refers to things other than gases as well, they're bouncing off of each other so frequently that they end up not really going anywhere. They're just constantly ricocheting off of their neighbor, and therefore no real net movement happens. And this is especially true in solids, because no matter how hot a brick of iron gets, it's never going to take off into the horizon just because it's hot. And it's because all the particles are scrambling in different directions at the same time, so the net motion is zero. So, that is the last piece of information that is officially Chapter 10. And with that, we will segue directly into what the book arbitrarily calls Chapter 11, which there'll probably be more review, still more review for you guys, if you've had much chem courses before. Yes, we did. If you have lab this week, which most of you would have based on my attendance records, then we've already used this at least once. If you've had this in chemistry, it also look familiar, then you remember what it's called.
Or what do you mean? Oh, the actual name?
Well, the principle at play here. Okay. Specific heat. Although the Q itself is heat, the designation of Q as a variable is heat. And that is thermal energy, so it's still measured in joules. Something to note, since we're now using Q as a variable, heat as a physics term refers exclusively to the movement of thermal energy, the transfer of thermal energy from one object to another. It's not the thermal energy itself, it's the flow of thermal energy. If you feel heat, technically speaking, you are feeling thermal energy either entering you or leaving you. Heat is technically then only barely a noun, it's more of a process, which is hard for my brain because I want to just use the word heat to refer to thermal energy. Just because in English vernacular, that's usually how we do it. But, just full disclaimer, heat is defined as the transfer of thermal energy. If thermal energy is not moving, there is technically no heat involved. So, the principle of specific heat informs us that as thermal energy enters or exits an object, its temperature is going to change based on a few factors. So, when you touch something that is a different temperature from yourself, due to the collisions between your hand and whatever you are touching, heat and thermal energy will flow from hot to cold, either out of your hand into the object or from the object into your hand. That's what the Q term is, thermal energy that either enters or exits. And the object in question will change its temperature, delta T, based on its mass, how many particles it has, how many atoms it needs to keep moving at a specific temperature, and C, specific heat, which refers to just the properties of a specific type of material when it comes to retaining heat within itself. Has anyone never interacted with, this is the same formula, has anyone never interacted with this before? Okay. Again, I have assumed, I went into this assuming that you had seen this before. If, in making that assumption, I skim over something by accident, please let me know and I'll refer back to it. I don't want to confuse you guys. I also just don't want to repeat things that you already know. So, within these notes, we have our very handy table of specific heats refers to the to the change in temperature of an object based on what it is made of. We are really only going to care about this first column in this class because that first column is joules per kilogram per degree Celsius, because we like kilograms in physics. I assume the second column is seen more in chem classes. You guys use calories in those? Okay. Do they use grams, 1 kilograms upstairs? That makes sense. If you're just weighing out a single tray of reactant. I think in physics we like kilograms because it makes all of our forces 1,000 times smaller and therefore less scary. And every material has a different specific heat. The bigger the number it is, the more thermal energy it needs to increase or decrease its temperature. And as the bigger the number, the more thermal energy it needs to change its temperature. The more joules per kilogram per degree Celsius that you need. And water, as always, is our ever-present anomaly. It is the single highest number on the table. It has one of the higher specific heats on the entire planet, which is good because since water takes a lot of heat to warm up, it's a very good heat sink, which means Earth is constantly dumping heat into the ocean, and the ocean absorbs it so that the land is not on fire. Similarly, because the ocean retains its heat for the same reason, it doesn't freeze in the winter. I think the tides help with that too. And the waves. So, this is review, then let us use and review this principle quickly. Where's the cap of this marker? It doesn't fit on the marker, so I keep setting it down somewhere. I'm going to lose it. There it is. I must have put it on the end and it fell off. So, when you boil water, you are inherently adding thermal energy to that water, and you want its temperature to change. So, the camping stove is 2.6 ounces, and it can boil 1 liter of water in an amount of time. So we have volume of water this is the starting temperature of that water at 70 degrees Fahrenheit. Boiling time is 4 minutes and 7 seconds. And we do know that we are dealing with water, so the first thing we are asked for is how much thermal energy needs to be added to the water to make it boil. If it's going to be boiling, we can therefore assume final temperature in Fahrenheit is going to be 212. But we prefer Celsius in this class. So, to get to Q, what's our next step?
Should we change 70 degrees Fahrenheit to Celsius?
Yes, we should. And I'll write that up just so that you guys have it in the notes. So we prefer Celsius in this class, and as long as we are looking at a change in temperature, we can use Celsius instead of Kelvin. yes, that tracks. That's just below room temperature. Thank you very much. So we now know temp final and temp initial is Celsius. What formula are we going to be using? Spoiler alert. Spoiler sure they're asking if I said just going to use it now.
Does your mass converted?
So yes, we are heating up water. We're told the volume of that water. Just off the top of your head, if you have 1 liter of water, should you be able to assume what its mass is?
Yes.
What would its mass be? Okay. So the density of, we established what a gram is, such that, and we established, the original metricists who set all the units set 1 gram and 1 liter such that the density of water is always, at room temperature, 1 kilogram per liter. So if you're told the volume of water, you can typically assume the mass of water. Yep. And it's the only material on Earth that does that. Water is just kind of a weird exception all around. So, you know the mass of water we're heating. We know it's delta T. We want Q, so we just refer back to our handy table for the specific heat of water. Q equals 1 times our specific heat. Water is, I remember waters because boy does it show up a lot. Delta T. Always final minus initial, which will give us a positive answer because we need more heat to get to boiling.
The specific heat, is that in joules or kilograms?
Joules. The way that I wrote it up there is joules per kilogram degree Celsius, which will give us our answer in normal joules. And what might that answer be? Yep. Which, scientifically speaking, is a lot. For comparison's sake, I think the smallest specific heat on the textbook's table is, yes, it's tin. No, it's gold. Oh, I forgot that was one smaller. So gold's specific heat is just ballpark range about somewhere between 30 to 40 times smaller, which means that its temperature, instead of spiking by 80 Celsius, would spike by 400 Celsius, and if the same amount of heat was added to it. So the properties of water, yet again, make life on this planet habitable. Yes?
I have a different answer.
I didn't see
Okay.
it.
Well, I know it's meant to be big.
Yeah, I don't.
Calculator. I don't have the number
I
written in
had
my notes.
275 instead of 229.
I was too.
Okay.
So I got 307,275.
307,275. 330,275.4. That is also what I have. I would not be especially bothered by being off by that small for a number this big.
Oh, wait. I mean, sometimes, yeah, wait. Try just the way you wrote it out, like doing that.
Because, I mean, I didn't like round it, I just like grab it from above. That's
Right.
it, You know what I mean?
Instead of plugging in 21.1, you took what the calculator had in it already,
Yeah.
which would be a more accurate answer, technically speaking. So
Isn't that kind of big of a difference? 70, yeah.
that would be a difference of like 50 joules, which sounds like a lot until you remember how tiny 1 joule is. I'd say snapping my fingers generates way more than 1 joule of thermal energy just from the friction. 1 joule is the amount of energy needed to warm up 1 gram of water by 1 degree Celsius.
Okay, yeah, I didn't grab it, and then it does get what you got, which I guess is.
Well, again, if I was grading it, I would factor that in on the assignment, on my grading sheet. As long as that would technically be like 1% off. For a number this big, 1% would be something wrong with this number instead of this number. So it's very, very close. It's only due to the rounding on this. And again, 50 joules would only be enough energy to warm up 50 grams of water by 1 degree Celsius. It's not a lot of energy, and so you lose way more than that to the air in this situation. I'm not too picky about it.
For the chart of specific heat, does the lower the specific heat of whatever material translate to malleability?
I don't know if it directly translates to malleability. Let's take a look.
Because I was thinking about how like the metals, like gold and
The lowest is gold, next lowest is tin, then silver, copper. So you're not wrong.
right?
There is a trend of malleability for solids at those temperatures. I don't think that's a good hard and fast rule. I don't think it's a direct scaling of low specific heat to high malleability. I don't think it's an exact representation because similarly, we've got aluminum is very malleable. You can bend that with your hands. And then within the same range, iron's fairly durable. I mean, it's still definitely harder than gold, but lead is not malleable hardly at all. It's more likely to break than it is to bend. And mercury is just a liquid.
Yeah. Okay.
Oh, lead's the lowest one on this table, actually. Just another reason we shouldn't use it. Meanwhile, yeah, aluminum's pretty soft. It's significantly higher than the other metals here. Beryllium,
So I guess it translates into conductivity, or what that?
you're right. There's a connection there too, because typically metals have the lower specific heats and they tend to conduct better. Again, maybe not a hard and fast definite ratio because glass is a semiconductor. It should conduct worse than aluminum. Aluminum's not the best conductor. Gold is definitely one of the best conductors on the planet. So you're right about that trend. And interestingly, the trend actually holds for water because pure water, pure H2O, isn't conductive. Got at least a couple of nods. Is anyone unfamiliar with that statement? it took me a while to wrap my head around that fact the first time I was told it, because I grew up in the era of Pokemon, and water always conducts electricity. That's just the rule in my head. But it only conducts because of the things dissolved in it, not because it itself is conductive. Which, again, goes against everything watching Pokemon ever taught me, because as soon as water is involved, everyone gets shocked and Pikachu does his thing. Second question on this particular slide, before we get too far away from the example we just did. This is sort of the next step. This is less about specific heat and more about thermal power. How many joules does the stove transfer to your cooking pot every second? So, we just figured out the joules that the water would need to an acceptable degree of error. And we know how long it takes the burner to make that water boil. So we have the timer between start and finish. How many joules does it output every second on average?
Is it on average because some seconds, like when it's warmer, it gives more joules, like that?
It would be an average because the rate of thermal energy always changes based on the temperature difference.
Yeah, okay.
Later this chapter, we'll look at the math behind why, but the hotter something is, the less thermal energy tends to flow into it. The speed of thermal energy transfer depends on the difference between one side and the other. If you touch something very cold to something very hot, thermal energy is going to rush over. But if two things are almost the same temperature, it's not going to be in any hurry to finish that process. Which is why, that's probably why a watch pot never boiled, because you're watching it when it's almost boiling, and it's just taking so much longer to get from 95 to 100 than it took to get from 20 to 95.
So we cannot just take the Q, which is now divided by the total amount of seconds.
You would. So we do have to find total amount of seconds. So how many seconds is in 4 minutes, and then that's 7.
So the answer would be 2.7.
Very good. So we have our heat over our time. It's going to be 3, 0, 2, something or other. Again, on a practical test key, I'd be accepting answers within a range based on how that rounded. I'm not too bothered by that.
I got 1,337.15.
As did I. Very good.
So joules per second, or,
Yes. So this, I ran out of room there. So this would be in joules per second. We literally divided joules by seconds. It is a rate of thermal energy transfer. Is there another term for that? For joules per second? Flashing back to last semester.
Would it be more?
Almost. Work is the use of energy itself.
are you gonna say what? No. Really?
1 joule per second is
I felt
1 watt.
Yeah.
So,
Because of the power, yeah.
yes, this is just power again. And you probably have in your notes, correctly so, power equals work over delta T. This is functionally exact. This is exactly the same thing. It's the same formula. Work being done is energy being used and transferred. Heat is also energy being used and transferred. It's just in a different state for a different reason. So when you are heating something up, there's some amount of thermal power transferring from one to the other. based on how long that takes. And yes, it is watts. Good job. You guys do remember things. Don't worry. It's in there somewhere. Okay. Yeah. Okay, so definitely have thermal power written in your notes. It'll come up again later, so don't forget about it. And before we end, rather than showing you another formula and just starting on that, we'll open up with calorimetry next time. Before we end, I want to talk briefly about something I said a second ago. The rate of thermal energy transfer depends on the difference between the two temperatures. So, I don't know, the example I was thinking of applies to a different thing.
Depends on the difference.
Difference between the temperature of the two objects. So, let's say, for example, your body, your skin, let's just assume the outside of your body, is approximately 75 degrees Fahrenheit usually. And you walk outside on a day like today, it's probably up to 32 by now, and you feel very cold. You feel that because thermal energy exits your body very quickly. Now, if you walked outside on a spring day, it might be 50, 55 degrees Fahrenheit, and that doesn't feel as cold, right? Because, well, again, I've mentioned we don't have a thermometer in our skin. We can only feel thermal energy exiting us or leaving us, which means the bigger the difference between us and whatever's going on outside of us, the more you will feel because more energy is leaving you faster.
What's the burning effect? When you're like so cold to burn?
That's more about nerves than I'm comfortable saying. On some level, eventually it might be water in your cells freezing. Eventually. I hope you never feel that cold. It's probably to do with, again, our nerves only detect thermal energy moving. No thermometer, just movement. I assume moving too fast in either direction might overload and trick them. Because if it's happening especially fast, there might be damage happening on some cellular level, and it might be too fast for the nerves to accurately track what it's doing. Kind of like how tickling and spicy food are a weird glitch in your nervous system. Again, not super qualified to speak on this, but tickling triggers a panic response because your body doesn't know what's happening. There's no nervous system response for tickle, so it short circuits the laugh and panic at the same time. Meanwhile, spice, like everything you taste interfaces with a certain cell on your tongue, and frustratingly, the spice zones overlap and glitch out with the hot temperature sensing zones.
And that's why you sweat.
Yes, you trick your body into thinking you're hot just because something is accidentally activating the heat nerves.
What? And you don't drink like something hot when you eat something spicy. That's horrifying.
That is horrible, and actually, because it's not actually temperature, drinking something cold doesn't help either. You need to neutralize whatever you ate that is activating those cells.
Salt, yeah.
Because your taste buds are activated by the molecular makeup of whatever you're eating.
Correct. You say salt?
Yeah,
I've heard of milk.
Milk, salt. Our water's like the worst.
Water is like one of the.
But yeah, that's just going to spread it around the rest of your throat. And you have more taste cells than just on your tongue, I think. Like, there's parts of your throat that feel spice. At least for me, I can't handle spice in the least. One of the schools that we used to teach at had a rather large amount of Chinese international students. They were great fun to interact with, and the cuisine in that part of the world is just spicy, most of it anyway. And so when the Chinese students found out that I was an absolute spice weenie, they went out of their way to find both American spicy food to feed me and imported Chinese spicy food to feed me. And then they recorded me reacting to it. All right. We will pick up tomorrow applying this principle to calorimetry. Do be finishing up the Chapter 10 assignments as soon as you're comfortable with those, and start the Chapter 11 assignments. And have a wonderful day.